Hello, everyone. Welcome to Physics 213. This is Lab 7, which is on wave motion and sound. So in this lab, we'll be looking at wave motion on a string, basically looking at what's called standing waves in a string. And then also we'll be looking at wave motion in the air. And basically it'll be the air that's inside a tube. And we're going to use that information to compute the velocity of sound, so the speed of sound in the air, right, in the lab room. Now, again, the original video that I recorded was done a while ago during the peak of the pandemic. So you may notice that some of the numbering is off a little bit. I don't believe it's called Lab 7. So if you're watching this now because you missed lab, make sure you use this particular handout for this semester, the actual Lab 7 handout. The video contains the same exact information. The only thing that might be different is sometimes the numbering is slightly different. So when you get to the questions, the numbering might be slightly different depending on what semester you're in, but the information again is the same. And the other thing you'll notice is that in the video, you're going to see a lot of this information filled in because during that semester that I recorded the video, students weren't able to actually collect the data. So I had to pre-collect all the data for them, and they basically just analyze the data, okay? So if you're watching this because you missed a course, the best way to handle this is to actually get the data from your lab partners from this semester so you can use their particular data in the tables here. But if for some reason you can't get that data, then you could always just use the values that you see in the video itself. Okay, but the information is exactly the same. The other thing I noticed that in that older video, the animations don't always come out great when you're watching the video, and I think it has to do with the frame rate. So in Brightspace, I will post the animated GIFs separately, so you can click on them if you want to actually see the animations better. All right, so what's going to follow is all the information for wave motion and sound. Thanks. Okay, so again, this lab is on wave motion and sound. And the first thing I want to describe is the mathematical equation for a traveling wave, a wave that propagates or travels. So traveling wave and this is sort of the general form of the equation. So it's y equals a times sine of 2 pi t over capital T plus or minus 2 pi x over lambda plus phi. So let me explain what each of these parameters represents here. So first of all, little t is simply the time, right? The time in seconds. X is going to be the horizontal position. So that'll be in meters. This is in seconds. This is in meters. The y is the displacement from the equilibrium position. So displacement from equilibrium and then capital A is the amplitude of the wave. That is also in meters. This is also in meters. Capital T is the period, right? The time for one oscillation. That's in seconds. Lambda is the wavelength. Again, in meters. And then phi here is the phase angle. So phase angle. And that would be in radians, right? Okay, so what does all this mean? Well, there's going to be two situations that we're going to be looking at. One of them is a wave on a string, so a traveling wave traveling down a string and then reflected back. And actually, ultimately, we're going to be interested in what's called the standing waves. I'll explain all that later. So wave on a string, and then a sound wave, like a wave in a tube, basically. So a sound wave propagating through a tube. So let me talk about a wave on a string first. So wave on a string, you can think of this as what we call a transverse wave. So transverse wave. So what does it mean for those parameters like the amplitude, the period, the wavelength, etc.? So let's say this is the equilibrium position of the string. And let's say I examine one little piece, one little particle of the string. And what is it going to be doing? It's going to be oscillating up and down. So this particle will do something like this, oscillate up and down. Well, this distance from the equilibrium position to the highest point or the lowest point, this is called the amplitude. So that's what we mean by amplitude. Okay, and actually any position from the equilibrium position is our y value. So that would be like our y value. The period is simply the time for one oscillation. So the time it takes that particle to go up, back, and up again. Okay, and then the wavelength, so let me draw this out again. Let's say this is my equilibrium position. Let's say the wave looks like this. If we freeze it for an instant, looks like that. So if I pick some point, right, along the x direction, let's say this point right here, I'll do it in red, and I go down the wave and I find another piece or another point or another piece of the string that's undergoing the same motion. It's the same distance from the equilibrium position and it's moving in the same direction. So that would be right here. Then this distance, so from here to here, that is called the wavelength. So this distance would be the wavelength. You guys are probably more familiar with going from peak to peak, but it means the same thing, right? It's some point on the wave where the string is undergoing some motion, and you go down the string and you find a location where the string is undergoing exactly the same motion. It's moving the same direction. It's the same distance from the equilibrium position. That's going to be the wavelength of that wave. Okay, so that's for a transverse wave, a wave on a string. What about a longitudinal wave or a sound wave? Okay, so in this case, for a sound wave, or a longitudinal wave, now you can think of it as you have you have a tube, right? That air can, or a wave of sound can travel, and the medium itself is going to be the air. Let's say this is a particle of the air, and this is the equilibrium position. Then that air particle can oscillate back and forth. Okay, so in this case, if I go from the equilibrium position to the furthest point that the particle goes, that's going to be the amplitude from there to there. And then if we draw out the entire tube here, if I have some particle, let's say some air molecule, it's a certain distance from the equilibrium position and it's moving in, say, this direction, and I move down the tube and I find another particle that's undergoing the same motion. So it's the same distance from its equilibrium position and it's moving in the same direction, then that distance from that particle to that particle would be the wavelength, okay, of the longitudinal wave. And then just as before, the time for one oscillation is going to be the period. So the period is the time for one oscillation. So that would be the time that it takes, say, this air molecule to oscillate back and forth. So we do it from equilibrium, furthest possible right, all the way left, and then back to equilibrium. That time would be the time for one oscillation, so that would be the period. Okay, let me give you guys an example of what a traveling wave looks like, and I'll show you some animations of this. So here's an example. Oh, let me do this in black. So example of a traveling wave. I want to show you why that equation actually leads to a traveling wave. So again, here's our mathematical equation. Y equals A times sine of 2 pi t over period plus or minus 2 pi x over lambda plus phi. So let's pick some nice easy parameters to plug in so we can actually do this out for a few values. So let's let the amplitude equal 1. Let's say the period, so this is really 1 meter. The period is, say, 1 second. Lambda is also, say, 1 meter. And then let's say the phase angle is 0. By the way, the phase angle just shifts that sine wave to the left or to the right so that you can account for the initial conditions. Right? In most cases, we can think of it as 0. All right, so if I plug in those parameters, then this equation simplifies to y is equal to sine of 2 pi t, and I'm going to use the negative here. That just means the wave is traveling to the right, and then 2 pi x. Okay, so what I want to do now is I want to plot this function from x equals 0 to x equals 1 meter. So that'll be along the horizontal axis, right, from 0 to 1. And then I want to plot it at particular times. I want it at time t equals 0, a quarter, a half, 3/4, and 1 second. Okay, so let's see what this looks like. Okay, so here I have the plot shown here. Um, you can think of it this way as the blue being the first one. So here's the first sine wave. And then a quarter of a second later, I have the red. And then I have the green. And then I have the yellow. So what's happening is this wave is moving to the right, right? It's propagating to the right. If you look at the peak here, you can see it's moving to the right, the blue, the red, the green, then the yellow. Let me show you actually an animation of this. So here's an animation I made up that shows that propagation. Will it work? No, hold on a second. So here's an animation where I simply plot the wave. Actually, in this case, I plotted it from 0 to 2 meters. So that's the X. And then I'm just increasing the time. I'm going from 0 to 2 seconds. And you can see that it's a wave that propagates to the right. Here's an example of a transverse wave. So you can think of this as sort of like the wave on a string. And if you notice here, right, think of each of these particles as being a piece of the string. They're just oscillating in place about their equilibrium position, right? They're oscillating up and down about their equilibrium position. But the disturbance, if you follow the peak here, it's traveling to the right. Okay, so that's what we mean by a traveling wave. Each particle doesn't actually travel, it just moves about its equilibrium position, it oscillates. But the disturbance is what propagates. And then for a longitudinal wave, let me show you that. So that's like this. If you look, again, if you look at each of these, think of these as air molecules, they're simply oscillating back and forth about their equilibrium position, but the disturbance itself propagates to the right, okay? Actually, I think I have a better animation of that. Let me see if I can find it. Oh, here it is. So focus on like this red air molecule here. It's just oscillating about its equilibrium position, right? It's not actually traveling down, but the disturbance, and they noted it here by the wave here, the disturbance is what propagates to the right, okay? You can think of the air molecules as being like compressed and then what they call rarefaction. So they're being compressed and then uncompressed, compressed, uncompressed, and so on. So it turns out that if you have a traveling wave, say traveling on a string to the right, and then it gets reflected from the boundary, so you have a reflected wave traveling back to the left. If you have the right conditions, and that basically means the correct length between the point at which is causing the vibration, the blade, and then where it reflects, the boundary, and you have the correct tension in the string, then what we can create are what's called standing waves that simply oscillate in place, okay? And the same thing for a sound wave. So if the tube is constructed correctly with the correct length, then we can create these standing waves of sound inside the tube. So let me give you an animation of what that looks like. Okay, so in this case, think of this as a wave on a string. So I'll start this animation. And you can see the red wave is the wave that's initially traveling to the right. And then when it hits the boundary, in our case, the boundary is going to be a little pulley that we have on one side. It's going to reflect, it'll invert and be reflected so that you have a reflected wave traveling to the left. And those two are going to add together to form what's called a standing wave. So the blue is the reflected wave. And then the result If I add those two together, I get that standing wave that's just oscillating in place. So red is the initial wave moving to the right, the blue is reflected, and then the black wave right there that's oscillating in place, that is the sum of those two. So that ends up being the standing wave. Actually, let me turn off the incident ray. So that was the one floating to the right and the reflected ray to the left. And then what you get left is just this standing wave that oscillates in place. So this is what we're gonna see when we adjust the string so that we can observe these standing waves. Okay, here's another animation that's very similar. Let's see if I can blow this up. There we go. Okay, so this is actually what you guys are gonna see. When we talk about one loop, this would be an example of one loop. So this side would be like the vibrating blade. This side would be like the pulley. This length would be our 1 meter. And we're simply gonna see a string that oscillates back and forth in place. By the way, these two ends, the places where the string don't move, so if you look at the two ends of the green wave here, these are what are called the nodes. So the nodes are locations where there's no movement of the particles. And then the place where the string moves the greatest, so right in the center here, that would be an antinode or antinode. Okay, and in this case, one of these, I don't know exactly which one. I think it's the red is the one that's the incident ray traveling to the right, and the blue is the reflected. Actually, let me speed this up. So you guys will see a wave that just oscillates in place back and forth. And then let me see if I can increase the, okay, and again, when you see one loop like this is what's called the fundamental frequency. So when we do the experiment with the string, you're gonna see one loop. If I click on next harmonic here, you're gonna see two loops, right, which is like a full wavelength. And then 3 loops, and then 4 loops. Okay, so again, the green, the thick green is the standing wave. Okay, so now I need to talk a little bit about the conditions for standing waves to be observed and how you're going to actually perform some of these calculations. Okay, so condition for standing waves to be observed. Let's say we have the standing wave on a string, and let's say we're observing 2 loops. Okay, so the left-hand part, I'll think of this as the vibrating blade. So this is the blade. And then the right-hand part will be the pulley. And the wave is going to look something like this, right? If we're observing 2 loops, it'll be something like that, okay? Now remember, places where there's no movement of the string, those are the nodes. So in this case, right here at the blade, or pretty close to the blade, right in the center, and at the pulley, those are going to be the nodes. So nodes. And also at the pulley. And then the antinodes are going to be places where the string is moving the greatest. So here and here. So there's 3 nodes and 2 antinodes in this case. Now, if you think about this, right? If you think about like a wavelength of a sine wave, then a node-to-node distance, so if I go from node to node, that distance is half of a wavelength. So that would be lambda over 2. Right, a full wavelength would be, think of a sine wave. It goes from here all the way back to where it repeats again over here. So a node-to-node distance is half a wavelength. So if I'm observing a particular number of loops, right, between the blade and the pulley, then there's a certain condition that has to be met, right? If I multiply the number of loops times half a wavelength, that has to equal the total length from the blade to the pulley, right? So the N here is the number of loops, and the L is the length from the blade to pulley. Right? If that condition is met, then I'm going to observe, either 1 loop or 2 loops or 3 loops and so on. I'm going to observe an integer number of loops, right? If that condition is met. Now, the nice thing here is I can rearrange this equation. I can solve this for lambda. If you solve it for lambda, you're going to get lambda is equal to 2L over N. Okay, and you're going to have to use that formula later and for your lab report whenever you're asked to compute the wavelength when you're observing 1 loop or 2 loops and so on. Just use that formula. So it's 2L over N. Okay, another thing about the traveling wave is we can calculate the velocity, and it turns out the velocity is simply, so V is velocity. You can think of it as displacement divided by time. So in this case, the displacement is like lambda, right, the wavelength, and the time is like our period. Okay, but usually the way people write this is they write it slightly differently. Instead of the period, they use what's called the frequency. So F is the frequency. It's a number of oscillations per second, right, or hertz. That's really equal to 1 over the period. So another way that we can write velocity of that traveling wave is simply as F times lambda. So it's the frequency times the wavelength. And that'll be in the correct units at the end of meters per second, which it has to be, right? Because velocity is meters per second. Okay, so now physically, what does the velocity of that traveling wave along the string depend on? Well, it actually depends on the tension in the string and something called the linear density of the string. So if you measure the mass per length of the string, that would be the linear density. So let me write that down here. So the velocity of the traveling wave on the string physically depends on the tension and the linear density. And the formula for it is going to be velocity is the square root of the tension over the linear density. So again, T is the tension in the string. And that's just in newtons, right? SI units, newtons. And then mu here is the linear density. So it's going to be in, well, just like regular density is mass per volume, in this case, linear density is mass per length. So it'll be kilograms per meter. So what we want to do is we want to rearrange this equation and solve it for the tension. So if I, excuse me, if I square both sides, so v squared is going to be t over mu, and then multiply both sides by mu, I'm going to get t is equal to v squared mu. But we can actually plug in for v because we know that v, the velocity, is, remember, it's the frequency times the wavelength. And then the wavelength, we discovered when we're observing one loop, two loops, and so on, is just equal to 2L over n. So I can put these things all together. Actually, first let me substitute in lambda for here to get a new equation for v. So v, the velocity, is going to be 2FL over n. That's another equation you guys will need later, so I'll box it here. And then finally, if I substitute in v into the equation for the tension, then I end up with the tension is equal to 2FL over n squared times mu. And then we could write that, if I expand that out, it's going to be 4, I'll write the mu first, F squared L squared over n squared. So you can think of this as the theoretical tension. So later when I ask for T theory, that's the formula you're going to use. 4 mu F squared L squared over n squared. Okay. By the way, another way that we can write this is we know that when we're observing one loop, so when n is equal to 1, right? So just one loop, then I can write the tension, I'll write T1 for T for one loop, is going to be 4 mu F squared L squared over 1 squared, but that's simply 4 mu F squared L squared over 1, right? So the 1 is gone. So another way of writing the tension for n loops is I could say, well, it's going to be the tension for one loop, because that is just the numerator here, right, divided by n squared. So for example, let's say I want to know the tension for two loops, T for two loops. Well, it's going to be the tension for one loop divided by 2 squared. Well, that's basically 1/4 the tension for one loop. So the tension, if you want to observe two loops, you're going to need like 1/4 of what the tension was to observe one loop. Okay, so let's look at the lab report itself. Now, of course, these labs are definitely modified from what they would have been if this had been an in-class experience. So what I did was I actually put all the questions in that I want to ask you guys, so you don't have to refer to your lab manuals. The questions will be built right into the lab report itself, okay? And again, I want you to do group lab reports, use the same members that are in your group that would have been there if had this been a lab done in class. So you're gonna have to work together, share files, however you want to do it. And only one person from the group needs to submit the lab report. I'm gonna set up an assignment in Brightspace so that you can just upload your lab report. Whether you want to do it as a PDF or a Word doc is fine. Probably a PDF would work best. And then I'll grade it and submit the grades, or I can actually post the grades on Brightspace so you guys will have the grades and get that feedback. Okay, so if we look at this lab report handout, there's some background information, which I talked about all this. If you want to read it more closely later, you can. Okay, so for the experiment itself, What you want to do first is you want to view the video in which I show you how the data was collected. So the first video involves the standing waves on a string. So I have the link here, right? You should be able to just, I think if you do Control and click on it, it's a Word document, or you can just copy that URL and paste it into your browser. So you want to view that video first. Here's the data table. So the length of the string between the blade and the pulley, that's just 1 meter, so that's given as 1 meter. The linear density of the string, the mu, that's given as 0.00075 kilograms per meter. And then the vibrating blade, its frequency, so the F is given, it's a constant, it's 60 hertz. So that blade was vibrating up and down or left or right 60 times a second. And then the data I collected for you guys was I had to figure out how much mass to hang from the string so that I was observing exactly 1 loop and then 2 loops, 3 loops, and 4 loops. So these are the mass values here. So I had to put 1.150 kilograms on the hanger. That's including the hanger itself, right? And then I observed exactly 1 loop. You guys will see this when you watch the video. I had to put on 0.285 kilograms to observe 2 loops, 0.130 kilograms to observe 3, and so on. And really, that's all the data that you had to collect. The rest of it is going to be calculations, and that's going to involve the questions here. So your first question is to calculate the wavelength when observing 1 loop, 2 loops, etc. So basically, you want to fill in the second column in the table here. So how do I find the wavelength? Well, remember the wavelength was simply 2 times the length from the blade to the pulley, right? That's given as a 1, divided by the number of loops that you're observing. Remember, n is always the number of loops that you're observing. So here, I'll do the first one. We can do the first one together. The wavelength for the first one here, when we're observing 1 loop, is simply going to be 2 times 1 divided by 1, right? Which is 2 meters. So this is going to be 2 meters. So you want to do that for each of these, right? When you're observing 1, 2, 3, 4 loops, and make sure you show me all those calculations. Okay, next, you're asked to calculate the experimental tension in the string, given that you observed 1 loop, 2 loops, 3 loops, and so on. Well, remember, since the hanger, right, I figured out the mass that I had to hang from the string. If I want to figure out the tension in the string, the hanger is not accelerating up or down, right? So the net force in the y direction has to be 0. Therefore, the tension pulling up must equal the weight pulling down, right? The sum of the forces in the y will give you 0. So the experimental tension is simply the weight. And how do I calculate the weight if I know the mass of that hanger? Well, it's just going to be the mass times g, right? In this case, we're using SI units, so it'd be this mass times 9.8, and that will give you the experimental tension. Right? And you can calculate that for each of those 4 conditions. Okay, next you want to calculate the theoretical tension in the string, and we just derived that, right? And remember, that depends on the linear density. It depends on the frequency, which is always 60. The linear density was a constant value. Remember, that was 0.00075. The L is always 1 meter. So you plug those in and then divide by the number of loops that you're observing. Okay, and that'll give you the theoretical tension in the string. And then once you have those values, you want to compare what you got theoretically to basically what I got when I did this experimentally, right? And we'll see how close that these values are. So compare the two by computing the % experimental error and show all these calculations, right? Show the 4 theoretical tension calculations and show the 4% experimental error calculations. Okay, next, question 4. Calculate the wave velocity. So remember, those standing waves consist of an incident wave that's traveling to the right and then a reflected wave that's reflected off. They have a particular velocity. So we want to figure out the wave velocity, how fast that wave was traveling on the string. Well, we derived that formula earlier. It was simply, well, first of all, it was simply F times lambda, but lambda was 2L over N. So if you put that together, you get that the wave velocity is 2FL over N. Okay, so that'll give you the wave velocity for each of these conditions when you're observing 1 loop, 2 loops, 3 loops, and 4 loops. And make sure, again, that you show me all those calculations. So based on what you discovered here from these calculations, or just thinking carefully about the formula here, you want to answer question 5. Question 5 says, how does the wave velocity for 2 loops compare to the wave velocity for 1 loop? So V2 equals what times V1? And it's going to be basically a fraction. So my hint is, what is that fraction that you put there in terms of, in place of the question mark? Is it, you know, a tenth, a half, an eighth? What is that fraction? Then you want to answer the question for 3 loops. How does the velocity for 3 loops compare to the velocity for 1 loop? And finally, how does the velocity for 4 loops compare to the velocity for 1 loop? Okay, then question 6, suppose your string has a linear density of mu, and you adjust the tension to observe 3 loops. So you do whatever you need to do to the tension so that you're observing 3 loops, right? So you have a standing wave and you're seeing 3 loops. If you were to use a new string that has a linear density of 2 mu, what must you do to the tension to again observe 3 loops? Okay, so you want to think about that, and I'll give you a hint. You want to look at this theoretical tension formula that will help you answer that question. Right, so that's question 6. And then part B is with the sound waves, right? So the wave in the tube, the sound wave in the tube. So here's the background information. It's exactly the same traveling wave equation, except now it's a longitudinal wave as opposed to a transverse wave. So let me bring up the picture here so if you can see this. So basically what's going to happen is the speaker was oscillating back and forth at a certain frequency. In fact, we're using 2 frequencies. We're using 500 hertz and 650 hertz. So think of it as like 500 hertz. So it's oscillating back and forth at 500 hertz. The speaker is right at the end of the tube. So really, this is a place where you can think of as an antinode, because the air molecules are moving back and forth the greatest with the speaker, right? The speaker is oscillating back and forth. The air molecules are oscillating back and forth. And basically oscillating back and forth at 500 times a second. So like this. And then if you go down the tube, you're going to have places where the air molecules don't move at all. So right at this node, the air molecule is not moving. Here it's moving a great amount again. That's another antinode. And right at the boundary is always a place where you have a node where the air molecule is not moving. So our goal in this experiment is to move this barrier. So this black bar right here, that's going to be a barrier. It's going to start at the end. I'm going to slowly move it out, and we're going to locate the positions of these nodes. So this would be like node 1, node 2, and so on. Here's another picture where I have more than 2 nodes. I have 3 nodes in this case. So we're going to locate the position of all those nodes. Now, if you think about this, right, what is a node to node distance in terms of a wavelength? Well, it's half of a wavelength, just like it was for a string, right? So the node to node distance is half of a wavelength. So ultimately, we're going to use that information to figure out the wavelength of the standing wave in the tube. And if we know the frequency, so like remember this is 500 hertz, the other one's going to be 650 hertz. If we multiply the frequency times wavelength, we can figure out the velocity. But what is the velocity of? It's the sound in air, right? It's the velocity of sound. So again, the goal is to figure out exactly where all those nodes are. So what you want to do is you want to watch my video. Okay, I do this for both 500 hertz and 650 hertz. And I explained how the data was collected, how I figured out where those particular nodes are. So this would be the link to that video. And if you look in the table here, these are the actual values of the nodes. Okay, so this would be this distance here, the 0.085, it's in meters, and it's how far from the end of the tube the first node occurred at. And this would be the second node, third node, and fourth node, etc. Okay, for the 500 hertz, actually, we could find 4 nodes. For the 650 hertz, we could actually find 5 nodes. Okay, so what you need to do is you need to, this is question 7, you need to determine the node-to-node distances for each frequency. So for the 500 hertz, you should find 3 node-to-node distances. And for the 650 hertz, you should find 4 node-to-node distances. So what does that mean if we go back to the table here? So these S's are what I'm calling the node-to-node distance. So how do I find the first S1 node-to-node distance? Well, it would be the position of the node, of the second node, minus the position of the first node, right? If I take this difference between these two, that's going to be S1. And then the second node-to-node distance would be the position of node 3 minus position of node 2. This difference, that would be S2, and then this difference would be S3, right? So that's all you're doing. You're finding the node-to-node distance by taking the difference between corresponding nodes. Okay, question 8 is simply, once you find those, and they should be fairly similar, you want to find the average node-to-node distance for each frequency. So you're just going to average these 3 values, and then you're going to average these 4 values. In this case, you're going to find 4 node-to-node distances, right, at 650 hertz. So average those 4 values. All right, now that you have that average node-to-node distance, you can compute the wavelength of the sound waves for each frequency. Well, remember, a node-to-node distance in S is half of wavelength. So the wavelength is going to be twice the average node-to-node distance. So you can fill in this table here. You want to find the wavelength for the 500 hertz condition and for the 650 hertz condition. Okay, so that was question 9. Question 10. Now that you have the wavelength, we can calculate the speed of sound, right? The V, the velocity, it's simply equal to F times lambda. Well, we know the frequency, right? It's either going to be 500 or 650. And we know lambda, the wavelength, which we just computed in question 9. So if you multiply those together, that will give you the speed of sound. And then question 11 is simply to average those two, because you're calculating for both. You're calculating the speed of sound for the 500 hertz condition and 650. Again, they should be very similar. In theory, they should be exactly the same, but hopefully they'll be close. So average them together, and that will be your experimental speed of sound. Right? That value will be your experimental speed of sound. Now, it turns out we can calculate we can also calculate what's called the theoretical speed of sound. And this actually takes into account the temperature of the room. So here's the formula you're going to use. So the theoretical speed of sound is going to be V naught times the square root of 1 plus the temperature in Celsius divided by 273.15. V naught is just a constant, right? Everyone's going to use this value, 331.36. And when I measured the temperature of the room, the day that I was in there recording the videos, it was around 20 degrees Celsius. So if you plug those values in, that's going to be the theoretical speed of sound. And then finally, we want to compare what we got experimentally. So our experimental speed of sound, like using the resonance tubes, compare that to what we just calculated theoretically for the speed of sound. And you're going to compare them by computing the usual percent experimental error, right? And again, make sure you show me all these calculations. And then that will be your lab report for Lab 7.